In this question, we are given an adjacency matrix A, which describes a Markov chain with 3 states. And in the first part, we are asked for the values of A, B, and C that make this a valid adjacency matrix. Remember, the defining characteristic of an adjacency matrix, at least in terms of how we define them in EECS 245, is that their columns must sum to 1, and the individual values in the adjacency matrix must be between 0 and 1. Why must the columns sum to 1? As a quick refresher, it's because the columns in an adjacency matrix describe the movement out of a state, and you must account for 100% of the possibilities when you leave a state. Let me show you what I mean by drawing out this adjacency, drawing out the corresponding Markov chain. Why don't I use a different color here? Let's suppose this corresponds to state 1, state 2, and state 3. So I'll have a chain that looks like this. The first column describes movement out of state 1. And this first component, 0.4, says 0.4 of the time, or 40% of the time, when I'm in state 1, I stay in state 1. The next component, 0.4, tells me 40% of the time when I'm in state 1, I move to state 2. That's what I mean by the first column describes movement out of state 1. And this last component, which is A, one of our unknowns, tells us A of the time I move from state 1 to state 3. And what must A be in order for this to be valid? Of course, it must be 1 minus 0.4 minus 0.4, which gives me 0.2. And so algebraically, I can complete the rest here. What must B be? B must be 1. And what must C be? Well, C must be 0. So the way I would answer this question is with A is equal to 0.2, B is equal to 1, and C is equal to 0. Okay, the next part of this question is asking us for the steady state distribution of this Markov chain, or in other words, the long run fraction of time spent in each state. Now this question poses it as a multiple choice option, and so I suppose we could just guess and check, but what are we guessing and what are we checking? Like, what is the constraint that needs to be true? And let me clear some things up here just to make the algebra a little cleaner. We had 0.4, 0.4, and 0.2, 0, 0, 1, and a half, 0. The key idea is that we are looking for eigenvectors of A corresponding to the eigenvalue 1. And notice, if I have an eigenvalue of 1, that 1 is sort of invisible, and if I don't write it, this just looks like I'm looking for a vector v such that if I multiply it by A, it remains unchanged. I get back that exact same vector, not a longer or shorter version of it. I get back that exact same vector. And this is what I mean by a steady state distribution. I'm looking for a vector such that it has already simulated all possible steps of this chain, and if I simulate one more step, it's not going to change the distribution of time spent in each of my states. In this question, we're calling this steady state vector x star. Okay, so we're looking for the vector that satisfies this, and so the multiple choice component at the end of the question, I would fill in with eigenvalue 1. Now the question is, what is that corresponding eigenvector? Again, I could do this by guessing and checking all of the multiple choice options, but just to illustrate how I might solve this methodically if this were a free response question, let's work out some algebra. So I'm going to write the matrix A once again. And let's suppose the solution vector is of the form, I don't know, x, y, z, where x, y, and z are scalars. They must satisfy this equality, that multiplying A by x star, the vector, gives me back that same vector x star. Now this gives me a system of 3 equations and 3 unknowns, though as we've seen in examples in class, there are infinitely many solutions, right? Because they all correspond to the eigenvector of A with eigenvalue 1, and if, you know, some vector is an eigenvector, well then double it is also an eigenvector, and triple it is an eigenvector, and negative 245 times it is also an eigenvector. So we pick among all of those the one whose components add up to 1, because we can interpret that as a valid probability distribution over our states. Anyways, how do we solve this? Well, the first line tells me 0.4x plus 0.5z is equal to x. The second line tells me 0.4x plus 0.5z is equal to y. What that tells me right away is x and y must be equal. And then the last line tells me 0.2x plus y must be z. So I know x and y must be the same because they're being described by the same expression here. So the easy way to solve this is to take this last equation and plug in x for y here. So I have 0.2x plus, instead of y, I'll write x is equal to z. That means z is equal to 1.2x. So my solutions vector consists of the components 1, 1, and 1.2, right? And how did I get 1, 1, and 1.2? I just said, well, there are going to be infinitely many solutions, but once I fix a value of x, well, then y has to be equal to it, and z has to be equal to 1.2 times it. So I just picked the easiest number I could think of, which was 1, so I got 1, 1, and 1.2. The issue is the numbers 1, 1, and 1.2 don't add up to 1, right? And this is not one of the multiple choice options in the question. So what I need to do is normalize this vector so that its components add up to 1, and how I do that is dividing each of the components by the sum of the vector, which here is 3.2. But if I do it that way, the algebra is going to get a little messy. So instead, the way I'll think about this is 1.2 is equal to 6 over 5. So really, I'm looking at the vector 1, 1, 6 over 5, which is proportional to the vector 5, 5, 6. By proportional, I mean it is a scalar multiple. These are scalar multiples of each other, 5, 5, and 6. And how did I get here? I just multiplied this first vector by 5 to nullify the denominator. And now what's the sum of these things? 10 plus 6, that gives me 16. So I'm left with 5 over 16, 5 over 16, and 6 over 16, which I think would reduce to 3 over 8. And you know I'm doing this live because I don't know the answer off the top of my head. Indeed, that is one of the options here on my iPad, so it looks like we did this correctly. Okay, big idea. The long run fraction of time spent in each state is the eigenvector corresponding to the eigenvalue 1 of the adjacency matrix. And among the infinitely many eigenvectors, for the eigenvalue 1, you pick the one whose components add up to 1 because you can interpret that as a probability distribution.